Hello. Thanks everyone for joining us today for an in-depth talk on REST API security. It's 10 a.m. on the dot here in California. I just wanted to let you guys all know that today's webinar is being recorded and we'll be sending out the link afterwards, along with the slides and any other reference material that Les goes through during his presentation. If you run into any questions or any technical difficulties during the presentation, you can use the GoToWebinar console to ask me or one of the other organizers for help. There's a questions tab, so you can use that to reach out to one of us, as well as any questions that you have, about the presentation or any of the topics. Just enter them in as you have them, and then we're going to save those until the end. We'll have about 30 minutes for Q&A at the end. So for our agenda today, Les is going to walk us through OAuth 2.0 and access tokens, JWTs, as well as authentication, authorization, and a bit more. Again, like I said, we'll leave 30 minutes at the end for any questions. Later this afternoon, we'll send out the recording and slides. And yeah, I'm Rami Champion, part of our marketing team at Stormpath. And Les Hazelwood is here on the line too, Stormpath's CTO and Apache Shared Chair. Alrighty, let's get started. I'm going to hand this over to you, Les.
Okay, can you hear me, Rami?
Yep, I can hear you.
Okay, thanks. Thanks for the intro. Hello, everybody. We'll get right into it. Before we start, I just wanted to explain, if you guys haven't heard of us or Stormpath before, what we are, just so you understand what we do and why we're kind of talking about REST API security today. Stormpath is a user management API service for developers. We're specifically targeted at solving all the identity management problems that you have to build in your applications that you deploy for your customers or on the internet. So we handle things like password security, authentication and authorization, data storage, data modeling, multi-tenancy. So if you've got different tenants or customers that you need to support for your application, we help automate that stuff. We also do multi-factor authentication, SAML support, both service provider and identity provider support, as well as OAuth 2, which we'll be talking a little bit about today. We have LDAP and AD Cloud Sync, so that you don't have to integrate with AD or LDAP. We do it for you. And probably most importantly is our technology is instant on, scalable, and highly available. We spend a lot of engineering effort at Stormpath to make sure that we have all of our systems in highly available configurations, and security is one of our top priorities as well. So give it a shot. We're free for developers. It doesn't cost anything to use this on our free tier. And we have support for all modern major languages. We have over 13 different language communities that we support now. So you should be able to get started with little effort. So what are we talking about today? We're going to be discussing HTTP authentication specifically, given that almost all REST APIs are HTTP based. We're going to talk about how the HTTP protocol supports authentication natively via what are known as schemes, authentication schemes. And we're going to support, or rather discuss, various different schemes and compare and contrast them, see what are the pros and cons of different schemes that are commonly used today. And then we're also going to talk about API key authentication. This is something that's important for people building servers or services over the web, why API keys are used, why they're different than maybe password-based authentication. And then we'll talk about token authentication. It's all the rage these days. Tokens for authentication in HTTP requests, maybe tokens for microservices. We can discuss how what that looks like and how people are using them. And finally, we'll talk about authorization, access control around REST APIs. But the first thing I want to cover is specifically around REST APIs, or rather, the presentation is going to be more focused on REST API concerns. So in the spirit of being RESTful, you typically want to eliminate server state. You want all state to be transferred between the client and the server, if possible. So we're going to try to eliminate server state. We're going to secure user credentials as best as we can. We're going to secure server endpoints, or URIs, or routes, or whatever you want to call them. We do want to try to expose access control rules to clients to help them understand what they can and cannot do with the server. That's going to be important for a lot of applications. And then finally, we're going to address what's important for many of us these days is how do we deal with single-page applications like JavaScript or Angular apps or React and mobile apps, iOS and Android. These are all called untrusted clients, and they have special concerns that you have to take into account when you are dealing with REST API security. So we'll talk about those as well. But what do we mean by HTTP or HTTPS authentication and authorization? A lot of times these two terms get confused, and it's easy to confuse them because the words look very similar. Let's clarify that right away so that we're all on the same page throughout the course of the presentation. Authentication is actually the act of proving you are who you say you are. So just because I tell you that I'm less doesn't mean that I'm actually less. You know, usually I could present to you a driver's license or a national passport, or maybe give you some information that only I should know. That is the act of proving my identity, that I am who I actually say that I am. And that is just general authentication. Authorization, on the other hand, is once you may or may not know who someone is, it's the process of determining if that person or actor or subject is allowed to do what they're actually attempting to do. So just because I'm accessing a particular URI doesn't mean that I should be able to access that URI. Maybe I need to have a particular role, like an admin role or something, to access a particular URI. Authorization is the process of determining access control. So those are the two differences. They're important it's important to know the differences when we're talking about HTTP headers. And that's what we want to start talking about now. So how do you do authentication, authorization, HTTP? Well, the HTTP spec has an authorization header, an HTTP header, that allows you to do both, actually, authentication and authorization. So we want to leverage this header. It's part of the spec. We don't want to use custom headers. There's no real need to, because it is part of the specification. We want to stay spec standard. Because it is a standard header, browsers typically don't require pre-flight CORS requests to support custom headers. Or typically, if you had a custom header, you might need to do a pre-flight CORS request in order to see if that header is allowed to be transferred to and from the server. So we don't need to mess with that, and custom schemes are actually easily supported. So even though it's a standard header, you can have custom mechanisms for authentication and authorization, and we'll discuss how that works in just a second. So how does it work? The authorization header and the authentication flow in HTTP is really based on what they call a challenge response protocol. And we'll illustrate what that actually looks like now. So in this example, I'm going to send a request, and I want to see this admin route. And so the server will then see if I am who I say that I am, or I've presented no additional information in this request to prove my identity. So the server will actually execute what's called a challenge response protocol. So the server is actually going to challenge in the response of this particular request by setting a www authenticate header and setting the HTTP status to be 401 unauthorized. Now, the word unauthorized here in the HTTP status code, it's a bit of a misnomer. It really means unauthenticated. And we'll talk about those differences a little bit later in the presentation. But 401 unauthorized really means unauthenticated. I don't know who you say that you are. So please prove to me that you are who you say you are. And they do that by setting the www authenticate header. And that header is composed of a string that looks like the following. There's some scheme name to identify what algorithm is going to be used for authentication, followed by some white space, followed by some stuff, some text. And that text can be anything that is meaningful for whatever that scheme is. So And we'll go through some schemes in a little bit, but the idea is that the scheme name identifies the algorithm to use between the client and the server. And whatever text that follows that algorithm name um, can be anything specific to that algorithm. So pluggable schemes are supported just by referencing different scheme names. So this is the challenge. This is step two. The server responds with this particular challenge, and then the client can say, "Oh, okay, I know you're looking for that particular scheme, so I'm going to re-request that route. I'm going to now specify the admin route. I want to do a get, and I'm going to present the authorization header followed by the scheme name that the server understands, followed by some stuff that the server understands for that particular authentication scheme." So this is the challenge response protocol. All HTTP authentication schemes are based, or flows are based on this header and this particular challenge response protocol. So they'll do a request, the server will challenge you for credentials or proof, and then the client in step three can resubmit that request with the proof that the server requires. So this is the high-level overview of the challenge response protocol. We'll dig into specific schemes next. So here we want to talk about HTTP basic authentication. It is the most basic form of authentication for the web. This is a good way to illustrate the challenge response protocol with real data. So again, we'll do a request to the admin route. The server will challenge and say, I need you to prove your identity. And so this is what a challenge could look like for basic authentication. As you can see, the www authenticate header is set. The actual word basic, B-I-S-I-C, B-A-S-I-C, is specified, followed by space, followed by this realm equals my app kind of string. And this is specific to the basic scheme. And the realm equals my app thing is basically a way for the server to tell the client the name of the application, so that the client can then tell the end user, do you want to log into the My App application? If so, enter your username and password, for example. Browsers do this with a little drop-down dialog. The realm equals My App is a way for the dialog to tell the user what's the name of the application. So the basic scheme is very, very simple, and it follows a particular algorithm that we'll cover in a little bit. But the client will, in step three on the re-request, say, okay, I'm specifying an authorization header. It is basic, followed by some white space, followed by some text value. This text value needs to be specific to the basic algorithm. So, and we'll talk about this particular algorithm in just a minute, but the schemes that I want to show you, and we'll actually cover in depth today, are the actual basic algorithm. We'll cover what digest schemes are. A really good example of a digest-based HTTP authentication scheme is OAuth 1.0a. We'll talk about how that works. In addition to digest schemes, there are bearer token schemes. For example, OAuth 2 is a common bearer token scheme. And we'll explain what that means, what a bearer token is. And then finally, there's custom schemes, how you might do a custom scheme or present a custom scheme for your own HTTP clients. So let's kind of dig in. HTTP basic is the one that we just covered a little bit. We'll actually show now how the algorithm works, so that anytime anyone talks about HTTP basic authentication, you'll know exactly what's going on. This screen is pseudocode. There's no particular programming language here. And by the way, this entire presentation is programming language agnostic. So regardless of your preferred programming language, this information is valid and relevant for all languages. But this is a little bit of pseudocode that simulates what how you might calculate this in your programming language. The basic scheme specifically is this algorithm. I need to take the raw username as entered by the user, concatenated with the colon character, and then following concatenated with the raw password text value as entered by the user. And I take all three of these things, concat them together, and then I will base64 encode the bytes of that string to get the particular base64 encoded scheme value. And then I can set the authorization header with the actual text word basic, followed by the white space, followed by the scheme value, this calculated base64 encoded username and password pair. So that's it. This is actually the basic scheme. It is extremely basic. and it's easy to calculate. Base64 encoding exists in pretty much every programming language, so this is easy for everyone to use. But there's also some cons associated with this. As I said, it's easy. It is supported by pretty much everything out there. But there are some difficulties or some challenges with this when it comes to security. As you saw with that text value, the raw password is entered by the user is always transmitted on every single request. And so if you're not careful about how you receive requests or how you respond to them, you can leak raw end users' raw passwords very, very easily. What if you set up a general logging framework that logs every request and all headers in a request as it comes across into your web infrastructure? Then you would essentially be leaking users' raw passwords into your logs. Anyone who can base64 decode those text values in the logs can now see end users' raw passwords. If a request was intercepted by a man-in-the-middle attacker for whatever reason, maybe you weren't using HTTPS, that raw password can then be seen by man-in-the-middle attackers. It could be seen by other software on servers that have access to those packets that are being transferred over the network. So that's a real concern too, that you have to keep these things extra secure. So essentially, HTTPS is always required in order to not leak these raw passwords over to anybody else. One of the difficulties, though, with HTTPS that a lot of people kind of forget is HTTPS is a network layer protocol. From the time the application sends the password down to the network, and from the time it hits the server and comes off the network and goes into the server-side web application, those passwords are not encrypted. The text values are not encrypted. Basically, encryption only happens at the wire level, at the transport level. So if there's any malicious viruses or bugs on the machine that can see these packets before they hit the network, then effectively the password is potentially exposed to an attacker if such a virus or program existed. Packet sniffers, for example, on a server before it hits the network can see this data. And so that's a real risk. Maybe your servers are sufficiently secured and you go through security audits all the time to prevent these issues from happening. But the reality is that HTTP Basic, because of these issues, is probably the least secure mechanism. But it is the most common. So it's a trade-off depending on the kind of data that you have to support and the type of clients that you have. And then finally, the clients must constantly retain a reference to the raw password. And so if the client is ever compromised, after authentication, it's always going to have access to that password, and an attacker could potentially see that raw password by attacking the client. So a lot of cons. The pros are good if you're reasonably sure that HTTPS is good enough for you. But for a lot of other people, this isn't quite good enough. In the evolution of HTTP authentication, it became evident that we needed a better, more secure way, and so digest schemes were invented instead of just basic. Now, what does that mean exactly? A digest is also known as a cryptographic digest or a cryptographic hash. Is a way of sending some data through a function and a password and getting a secure value, or rather a value out of that function that only can be computed using that particular password. But the output, what's known as a digest, is not considered itself a secure value. You can send that over the network without any fear of anyone intercepting it and trying to use it as a password. It's a one-way algorithm. You can't take that value and see what the raw password was. And so with the digest scheme, people started basically computing these digests, these cryptographic hashes of the request itself using a password that's known only to the client and to the server. Then you can take that digest and you can set it, as a custom scheme in your authorization header. So this is an example of what a client might do to compute a digest and send that digest value into the server. In this case, we're just using an example, fake scheme called foo, but the ability to just append that digest is possible because you can do custom schemes in HTTP. So this is what the client does. But if you look at here, the value of the authorization header is just the digest itself. It's not the raw password. So the password itself never gets transmitted over the wire. So how does this, if you're not sending the password over the wire, how does the server know to trust the request? And the answer is because there's a shared password between the client and the server can go through the same calculation once it gets the request. So here's an example of what the server pseudocode logic might look like. Maybe it'll look at a certain request header and find out who the client is, and then for that client, find out that client's password. And then it will calculate the same hash that the client did using the request and the password that it knows it's associated with that client. And so that will result in what we're calling here a server computed digest value. And so they can compute the server computed digest value and then compare it with the value that's in the authorization header. And if the client specified value is the exact same as the server specified value, the server knows that only that client could have created that digital signature, and it can trust the request. If the signature is different than what the client sent over, then the server knows that maybe it's been tampered with, maybe it was an expired password, any number of reasons, but it shouldn't trust the request to go ahead and send that 401 challenge, that error, to the client to let them know, hey, I need you to authenticate with the mechanism that I understand. So digest schemes are great in this regard because they don't actually send the raw password value over. And while this has been pseudocode, here's an actual example of a real digest scheme that's used in production. I think Twitter still uses this today. But they use the OAuth 1.0a scheme, which is a digest-based scheme, where they take a bunch of data, a bunch of request headers, they put them all in a specific order, and they hash it. They hash all that data with a secure hashing algorithm known as HMAC. And they expect the client and the server to compute the same output to make sure that the data is the same between the client and the server. So this is a real example of what OAuth 1.0a looks like. The client would send all of this data over as part of the authorization header, and the server would be expected to use this information and calculate the same digest, or same signature. And as long as the two are equal, the server could trust the client. But there are some problems with this. As you can see, there's a huge amount of information here. A lot of it is based in cryptography and digital signatures. And so let's talk about some pros and cons of digest schemes. In our estimation, digest schemes are most definitely probably the most secure mechanism that exists for HTTP, because the password's never sent over the wire. And because the password's never sent over the wire, it means HTTPS is actually not required with this type of authentication scheme. However, that doesn't mean that you don't want to use HTTPS potentially. If the data that you're sending in the request response body, the request body or the response body is considered sensitive information, of course you still want to use HTTPS to keep that data secure. I'm just claiming the actual digest value itself doesn't necessarily need HTTPS. So that's kind of nice depending on your use cases. Most people today use HTTPS, so that's not that big of a deal. But my point is that because of the cryptographic properties of the digest itself, HTTPS isn't required. It can guarantee end-to-end HTTP message authenticity. HTTPS cannot do this. A lot of things, again, as I mentioned, HTTPS is a network-level protocol. It can't guarantee that the message has been tampered before or after network transit. So HTTPS does not make those guarantees. Digests that are specific in the application and inside of the web server, they can do this. That is known as full end-to-end authenticity. HTTPS cannot do that because it's restricted to just the network layer. And it's also not susceptible to man-in-the-middle attacks. If there's a man-in-the-middle that receives or can see the data between the client and the server, there's nothing that it can do cryptographically to simulate what that digest would be or change the digest and have the server still recognize it. And so because of all of these benefits, we believe that digest schemes are the most secure from a data security perspective. So maybe if you're in banking or finance or healthcare, digest schemes could be really valuable to you because of these additional cryptographic properties. The problem with digest schemes, though, right, there's always a catch. Digest schemes are very difficult to design safely. You have to really, really know cryptographic security, or rather security and cryptography. You have to understand how digital signatures are created, how they're derived, how keys are derived. And so if you're not in the back, or if you don't have a crypto background, this can be very difficult to do. Even people with crypto backgrounds have difficulty designing hashing schemes. Um, because of that level of knowledge and complexity, they can be very difficult to understand and use, very difficult for clients to use. Um, and because of that complexity, you almost always need to have your own libraries, or rather implement libraries across many programming languages, so non-security or experts can actually use these algorithms. And they're harder to implement. You have to make sure everything is in exact order, every byte is represented accurately. There's a lot of effort to be done there. And a client still needs to retain a constant reference to the password, because they're always calculating the digest before they send every request. So with server clients, if server is talking to another server, this is usually okay if the servers can be seen as secure. Browser clients or untrusted clients, maybe not so much. You typically want to reduce the amount of time those clients actually have to see the raw password value. They could be decompiled. There's all sorts of network reasons also why you might want to do that, or keep them safer. So pros and cons of digest schemes. We'll talk about bearer token schemes next. So moving on, we've talked about basics so far. We've talked about digest-based schemes. Everybody these days is really talking about bearer token schemes. I need to do what, you hear people saying token authentication or microservice-based token authentication. They're really talking about bearer token schemes. And what does that mean? A bearer token scheme is basically setting the authorization header with the actual word, with a value that starts with the actual word bearer, B-E-A-R-E-R, followed by some white space, followed by some opaque token. You don't really know what that value is. You don't know what's in it. It is opaque for the most part for anyone who's not an application developer or interacting with a web app. This can be any value, really, a string. But what does it look like in practice? So while it can be any random string, it can be whatever you want, in reality, you still should be cryptographically signing these tokens and preferably expiring them. You don't want them to exist for eternity. You don't want them to be tampered with, right? You don't want some man in the middle or packet sniffer to be able to see these values and change them. So they themselves should be cryptographically signed to make sure that you can prove they haven't been changed or tampered with in transit. So while it can technically be any string, really best practices are make sure that whatever that value is cryptographically signed and expires after a certain amount of time. Here's a real-world example of OAuth 2 bearer token. So we're setting the authorization header with the word bearer followed by some really long string that extends many different lines. The value here isn't really that important in this example. We'll dig into what this actually means in a little bit, but again, it's just a random long, from our perspective, a random long string that has some sort of meaning for the server. And so the client, once it gets this token from the server, can just set this as the bearer header on all outbound requests, and the client, as long as this token is valid, as long as it hasn't been expired, the server can just trust that whoever owns it, whoever is bearing that information, is trustworthy. So, this is a little less secure than digest-based schemes, because whoever sees this value can use it to represent an authenticated user. But there are ways to mitigate some of those risks. So let's talk about pros and cons of bearer token schemes. They are easier to use than digest-based schemes because you don't have to go through some convoluted algorithm of exactly how to align all of your authorization headers and all that information in just the right way to make sure that the signature is calculated correctly. When it comes to the actual format of the bearer value, again, it could be any string, but a de facto standard has emerged over the last couple of years, and that standard is known as JWT, JSON Web Token. Most services these days that use bearer tokens are using JWTs because of the benefits that they have, and we'll cover those in a little bit. These bearer tokens themselves can contain state within that string, which means that technically you don't need server sessions anymore, at least to represent authentication state. And that's a really great thing for scalability. If you don't require a server-side session to be synchronized across web servers, and the state is managed by the client by just holding on to that bearer token, you can get much, much better scale. Many more web servers can be deployed without having to maintain server-side state. And that's really great for performance and scalability. Also, bearer tokens, once created, are different than maybe the initial password that was used to acquire the bearer token. So that means that the client doesn't need constant access to that user's password or client secret. And just the bearer token can be used. So that's really nice that the password doesn't have to be exposed on every request. But there are some cons in that HTTPS is always required because, especially during and after login. So once you acquire a bearer token, you never ever want to downgrade from HTTPS to HTTP. Because again, whoever sees that bearer token can just use it themselves as their own security token, and they can set that as their own bearer header in an outbound request and simulate the user that created that bearer token. So bearer tokens themselves should be seen as secure values that shouldn't be seen by third parties, just between the client and the server. So you always want HTTPS. Granted, that's not that big of a deal nowadays. Most people use HTTPS for all communication. Because the bearer token itself does not represent a signature across the whole request, it cannot guarantee HTTP message authenticity. In other words, a request that's been authenticated with a bearer token cannot prove to the server that somebody else didn't change the request body or add a header or remove a header. Digest schemes can do that, bearer token schemes can't. Or at least no currently proposed digest-based scheme for bearer tokens can do that. So they are susceptible to man-in-the-middle attacks. You never want a man-in-the-middle to see a bearer token. And token creation and renewal workflows can be complicated and confusing depending on your use case. OAuth 2, as a flow perspective, does confuse a lot of people. Basically, I've got a username and password. How do I send that into the server and exchange that for a bearer token, and then I can use that bearer token for all subsequent requests? How do you do that? What query parameters are required? Maybe response body, what does that look like? That can be confusing depending on who you are, your background, and how much exposure you've had to this. So, there's a little extra complexity added, I guess, when it comes to using bearer token schemes. When you're using these things in browser or mobile environments because they're untrusted devices, you still need additional security. You still have to go through your origin checks. You still have to do CSRF protection. The need to do those things does not go away when you use bearer tokens. Bearer tokens, because they can be seen by third parties, still need to have those additional checks in play to keep them safe. And again, token content, like what's in the token, is not really a standard. Applications can open themselves up to attacks if they're not careful about the kind of information that goes in the token. So if an attacker or a third party could see inside the token, apps need to take care to make sure that the data in the token is not considered secure data. So you would never want to put a password, for example, inside a token, or some secret value that's only relevant for that user. So you still have to be careful about what goes in the token. And finally, we'll talk, when it comes to schemes, we'll just wrap up really quickly around using custom schemes. We recommend, for most people, to not use custom schemes. If you are going to do a custom scheme, you should really only do it if you really, really, really know what you're doing. Seriously, there are a lot of security pitfalls in using custom schemes. It can be very dangerous if you're not aware of the cryptographic implications of what you're coming up with. So we recommend that most people don't do that. Even if you do go ahead and create a custom scheme, it won't be standard, right? There's no internet standard for whatever your custom scheme will be. So if that's the case, you essentially have to provide your own client libraries that understand that scheme so that your customers or end users can use your libraries to communicate with you using that scheme. That said, Stormpath does have its own custom scheme. We are a security team. We know the implications of this stuff. One of the nice things about our scheme, if you're using, or if you use one of our REST clients, for example, to talk to our REST API, our scheme actually authenticates the entire HTTP message. All the request headers, the body itself, the entire message is guaranteed to not be manipulated in transit, even before or after HTTPS transmission. Even OAuth 1.0a does not do this. OAuth 1.0a will guarantee authenticity of the headers, the HTTP headers in the message, but not the body. Stormpath does guarantee authenticity for the whole message. We use nonces to prevent replay attacks. We use key derivation algorithms and HMAC SHA 256 for the digest algorithm. And so we've gone through a lot of security research to do this stuff, and we have customers in healthcare, in finance, and Department of Defense. So we go through these extra steps to guarantee these extreme levels of security for our customers. If you're curious how this works, or you might want to use it yourself, just go to our GitHub page. It's github.com/Stormpath. You can search for the actual word SOC1 in any of our SDK projects, and you can see the algorithm in any number of the languages that you might be curious in: Ruby, Python, PHP, Java, .NET. It's all there. So if you're curious what a custom scheme looks like, you might want to check this out. Okay, API key authentication. We just talked about bearer tokens and basic schemes and digest schemes. What about API keys? Where do they come into play in all of this? Here's an example of what an API key might look like. There's this ID, and then there's this associated secret, and as you can see, the ID and the secret are really, really long compared to usernames and passwords. And there's a reason for this. API keys, compared to at least end-user passwords, there are more benefits associated with them, at least from a security perspective. There's far greater entropy, meaning source of randomness, when you're using API keys. Because the ID is super long, because the secret is even longer, there's much more entropy, there's more randomness when creating these values, which means they're much, much, much harder for an attacker to try to discover these values via, say, brute force or rainbow table attacks. It's very difficult. The more entropy you have, the harder it is to brute force. API keys are great because they're password independent, meaning, and this is crazy, I've seen a lot of REST APIs where your raw username and password that you use to log into, say, an admin console is the same thing that you use to authenticate requests to that company's REST API. And that's terrible, because what if you change your password? Maybe it's been exposed, maybe you forgot it, and you want to change the password. Well, you can do that in the admin console, for example, but the second you do that, now all of your integrations with the REST API start failing because the password has been changed. So don't couple your passwords to your user passwords to your REST API. It's a terrible, terrible idea. People get very, very frustrated if they change their passwords, and all of their integrations start breaking. So API keys are nice because you can assign an API key to a user account, and the user can rotate their API keys. They can create new ones, delete them, and use those to authenticate against a REST API instead of their raw username and password. So that's really nice. You can also associate scope with API keys, meaning even though there's a user account with an API key, maybe one API key can do 10 things and the other API key can only do 5 things. If you wanted to, you could attach permissions to individual API keys regardless of the user account. So that's nice. You can change scope depending on that. They typically tend to be a little bit faster than normal usernames and passwords. Usually, raw usernames and passwords undergo very computationally complex algorithms to slow things down on purpose, because you don't want a brute force attacker to be able to try to log in 100,000 times for a single user account within a second. Usernames and passwords typically tend to be slow, using algorithms like bcrypt or scrypt, where speed or slowness rather is actually a benefit there. API keys, typically because of the greater entropy and hopefully the more secure model around how to store them, you might not need to go through some of those slow techniques, and you can use faster algorithms. You can limit exposure with API keys. Typically, they tend to be files, hopefully, that are downloaded, and you can change the read permissions on that file to make sure that Nobody else in the world can read them other than the person who's downloaded the file. Passwords are often copied around or pasted around quite a bit, so maybe there's limited exposure with API keys, and that's a good thing. And finally, you can always associate you can have traceability with API keys. You can see for a given API key, what are the API calls that were made, how was it used, when was it last used, see if API keys are being rotated. There's a whole lot of benefits around API keys over just raw usernames and passwords when it comes to REST API specifically, that we strongly recommend, especially for server-to-server communication. If you have a server that's talking to another REST client, or sorry, REST API, definitely use API keys. There are a lot of security benefits over passwords. So, I kind of just described all this stuff. We'll just fly through this slide. An important point, though, is it is important that API keys, or at least API key secrets, are never embedded in untrusted clients like JavaScript clients in browser apps or iOS or Android apps. Those secrets could be seen by any third party that can load that application. And iOS and Android apps can be decompiled. You don't want that secret to be seen by an attacker. So never embed API key secrets in untrusted clients. They should really only be used for server-to-server communication. So how do you do authentication with an API key? You can use basic. For example, here's the same basic example that we saw earlier, but instead of a username and password, we're just replacing it with API key ID and secret. This would work just fine. Your server would need to be able to understand the difference between an API key ID and a username and password. Most systems, they can do that just by the length of the values. But, you have to be aware of one versus the other in order to do this correctly. So this is just a simple example. You don't have to use this particular basic authentication. There are other ways of using API keys with authentication. So feel free to ask questions about that. I want to move on to token authentication now, which is what a lot of people are excited about. Token authentication is the process of proving your identity to the server, and after you do that, the server gives you a token that then you can use for all your subsequent requests. So that way you're sending the token across the wire every request instead of a raw password or an API key secret. And that's really nice because the password and the token can be decoupled, right? And things like daemon accounts or microservices or things that might not be tied to a human being all the time can use tokens instead of raw passwords, which is convenient. One question we see in the context of token authentication is why not just use session IDs? Session IDs are kind of like a token, right? So aren't they good enough? And the answer is kind of not really. Session IDs, for one, they're pretty opaque and they have no meanings in and of themselves. So most session IDs are just like a UUID, which is just an ID pointer to some data somewhere in a database or a distributed cache. And you can have that, but if you have a service-oriented architecture or a microservice-based architecture, you might need to hit a service every time you see one of these IDs. So if I get a UUID, I need to go hit some centralized ID dereferencing service that says, for this ID, give me all the data associated with it. If you have to do that on every request, that can really slow down your architecture if you have all these different services hitting the same ID service. Unless that service is built for extreme scale, like Stormpath, for example, then you might come into problems. But also IDs, because they're opaque, a client can't take that ID and look into it. It can't see any information inside of it. It can't leverage it for its own benefits and its own needs, maybe to customize a UI, for example. It can't do any of that with a session ID. And finally, they are susceptible to CSRF attacks because browsers will automatically send these cookies as the cookie header without you requesting it. They will always do that, and so you have to be careful with CSRF concerns. So you still need to employ anti-CSRF prevention measures, maybe using synchronizer tokens or whatever. But you still have to be aware of these issues if you use session IDs. So they may not be perfect. Probably the biggest issue, though, is really server state. If you're trying to build a scalable application and you need to replicate sessions across a distributed cache or a distributed database, that's a real I/O that happens on every request. That is very expensive at scale, very expensive. So it's really not great for distributed or clustered apps. It's harder to scale. There's just a lot of complexities involved with session IDs. So um, there has to be a better way, and that way, at least nowadays, is token authentication. A lot of people are getting rid of their sessions and moving to token authentication because tokens can store information beyond just an identifier. So if that's the case, how do you actually get one of these? And we'll show you some examples of how OAuth 2 does it. In this particular example, we're going to show an example of a single-page JavaScript application talking to your server. And the SPA wants to get a token from your server. So here's one example. The SPA or Angular client or JavaScript, whatever you have, or iOS, Android, it doesn't matter. We'll send a post to a token endpoint. This is the OAuth 2 protocol, by the way. We're just showing you a very simplified request. But you can send a post to a token endpoint, and you want to specify in OAuth terminology this thing called grant type. In other words, what type of authentication am I performing? And in this case, the grant type here is password, meaning the client is sending a username and password, and as you can see here, there's also a username parameter and a password parameter. Sending it as XForm URL encoded content, and the server can look at this and say, oh, it's a password grant type, there's username and password, I'm going to do username and password authentication. But as a response to this particular post, I can give a JSON body, in this case, with an access token and a refresh token. And maybe this thing expires in 3,600 seconds, which is an hour. And you can have other data as well in the response. But that's basically how OAuth allows you to get tokens. You can post to the token endpoint with the username and password. And in return for this, you will get a nice access token that you can then send as a bearer header on every subsequent request. So this is step 3. After I've gotten my token, I'm setting it as the bearer header in all of my future requests. And so that's good enough for the server to know that, that only the client could have gotten that bearer token if they've used the appropriate authentication. So that's a very simple way of doing that, but you can also do it with API keys instead. So this is another OAuth 2 example. Instead of the password grant type, I'm using what they call client credentials. And so in this case, I'm saying I'm not using username and password. I'm using a client ID and a client secret that came from my API keys. And this authentication happens in a similar way that username and password did. It just uses an API key. And in response, they'll get the same access token and potentially refresh token. So you can use many different types of authentication, different schemes, if you will, or in OAuth speak, different grant types, and you will get back access tokens that represent that user account. So this just shows you an example of a way of changing different requests to get back different responses. So how does a server actually create this token? You know, we're talking about, this is an example of a client flow. How does a server actually create a token to give back to the client for subsequent requests? The answer here really is, as I said earlier, JWT has been emerging as the de facto standard for representing bearer tokens. JWTs are nice because it's basically a JSON object that is then serialized and compacted into a base64 URL string that can be used in query parameters or headers. It's self-contained, and within that data, you can have meaningful information. Basically, anything you can put in JSON can be inside of a JWT. So that allows you the freedom to put all sorts of goodies and information inside of these things. And then once it's been compacted and digitally signed to prevent tampering, that token then represents a whole wealth of information that you've stored inside of it. And most OAuth 2 implementations these days use JWTs as their access tokens. You can also store them in cookies, so that's really nice. You specifically secure-only, HTTP-only cookies. You typically don't want browsers or JavaScript to be able to manipulate those or inspect them. But if you do store them as cookies, all those security rules still apply. You still need CSR protection. You should be doing origin checks. But the really great thing about JWTs is that you can entirely replace your session concept with a JWT. Because again, it is a JSON object. Anything that you might have stored in your session, you can store in that instead, and the client will be sending it across the wire on every request, so the server doesn't need to maintain the server-side state anymore. Really, really beneficial, especially for REST APIs that are trying to be stateless. So let's dig into a JWT a little bit more to see how they can be beneficial and why servers and clients can derive benefit from them. If you look at a JWT, it looks like just some kooky, ugly string. Doesn't have any inherent or intrinsic meaning just by looking at it itself. But what's interesting about JWTs is at least signed, digitally signed, cryptographically signed JWTs, is this information can actually be broken up into chunks. There's a header followed by a period, followed by some body, or these are known as claims in the JWT world, followed by another period, followed by a cryptographic signature. This is specifically known as a JWS, a signed JWT, that has 3 parts, and period, this actual period character, is the delimiter between the header, the body, and the cryptographic signature. We won't talk about JWE encrypted JWTs today, but there's also JWT as a spec also supports encryption. It's got slightly more tokens, more parts than just these 3, but that's another talk for another day. But you can break these up into chunks, and the interesting thing about these is that if you base64 URL decode each one of these chunks, you actually start seeing some good information. So in this example, we've base64 decoded the previous text values, and now we see, oh, the type of resource is a JWT. It's specifically using the HMAC SHA-256 algorithm for its digital signature algorithm to make sure nobody's tampered or changed the token in any way. And the claims is really the interesting stuff. Has a whole bunch of information that the application can find useful. And the cryptographic signature below is, it's a bunch of random bytes that's used for digital signature verification. But if you look in the claims, that's where you're going to get all the good information that the server can then use to find out who this user is. The client might even be able to inspect it for information to help maybe render some user interface components. All sorts of good stuff in here. And if you go through these fields one by one, you can figure out more information, like ISS means the issuer, like who is responsible for issuing the token. When did the token expire? If it expires in a certain amount of time, it can't be used anymore to authenticate against the REST API. And that's a good thing because you want to limit a potential exposure if someone else was able to get access to the token. The subject is who it represents, meaning what's the user account or the identity that's represented by this particular token. And scopes are interesting in that they can basically be a list or a space delimited list of permissions of what the token bearer is allowed to do. Can they view their own information? Maybe can they buy something off the API? This could be anything that's relevant to your application. But the idea is that you can embed permissions inside of these things, and OAuth calls these permissions scopes. But the idea is you can leverage them in your own app for access control decisions, which is really, really nice. So one of the things about JWTs are nice is that they are implicitly trusted because they're cryptographically signed, meaning nobody's been able to tamper with them. So the server can trust if the signature passes or if signature is verified, you can trust the token. They are structured so that you can put a whole bunch of relevant structured data that might be usable across your services. And because there is a scopes concept, you can inform your client about simple or basic access control decisions. What permissions do they have? Can they do X versus Y? And of course, the big one is that they're stateless. You don't need to maintain session or cluster state around this identity, around the token, because the client's sending the token in on every request. I should note about the scope, though, is while a client may be able to see the scopes and permissions, the server still needs to enforce access control decisions on every request. So even though it hasn't been tampered with, you still need to verify the stuff locally. You can't ever trust that based on just what what a client sends over. So what's the catch? If these things are so perfect, nothing's perfect. So what do we have to take into account? You can think of implicit trust as a trade-off. In other words, if anybody gets access to a token, they will be able to do whatever scope is associated with that token. And so if I'm a man-in-the-middle attacker, or I'm a virus or whatever, and I get a hold of one of these tokens somehow, I can use that token for as long as the token is allowed to impersonate that user and do whatever that user can do. And so because there's this notion of implicit trust, what most people do is they assign timelines to these tokens, meaning they should only be alive or usable for a certain amount of time. For some applications, that can be as few as 5 minutes, at the end of which they'll need to get a new token. And that's what refresh tokens are for, where I have an access token that's going to die, so let me use the refresh token to go get a brand new access token. That's another talk. We won't have time for that today, but that's what refresh tokens are all about, is acquiring new access tokens. And so if my access tokens are only alive or only allowed to be used for 5 minutes, then I can get new ones every 5 minutes. In some cases, I think like Facebook, their access token is usable for 180 days, maybe even longer. So that's like half a year, if not longer. And so depending on your problem domain, you can change the time to live for these tokens. A banking application might want to use digest schemes entirely, not use bearer tokens. Maybe a more secure app can use bearer tokens, but maybe they're only allowed to be used for within 3 minutes, and you have to get new ones after each 3-minute period. Maybe it's a social network, and they're not storing credit card information, so maybe a year and a half or half a year is perfectly fine. But the idea is that you get to choose how long these tokens are valid for based on your security preferences. Again, if they're represented in cookies, you still have to secure those cookies, make sure that they're HTTP only, secure only. And because JWT can represent any JSON information, you really need to be careful about what you store in the JWT. So you don't want to store things like passwords or social security numbers or anything that's considered sensitive. Maybe like a user ID is perfectly fine. Maybe their first name, person's first name, maybe their last name, it could be fine. Just don't put whatever you consider sensitive inside of a JWT, and you should be okay. All right, so those are all the things that we wanted to discuss around authentication. We'll close up with authorization before we discuss or open the floor to questions. Authorization is really, again, the act of enforcing access control. Who can do what? JWT claims are nice because that scope field, again, lists a set of permissions for that user. And so if the server verifies the digital signature on the token and verifies it hasn't been tampered with, then it can do those permission enforcements inside of the REST API. So maybe I go to /admin and I can do that because I have the admin scope. Roles and permissions are constantly referenced in the concept of scope. And whether you represent scope to contain a list of roles or a list of permissions is entirely up to you based on your application and your security model that you have in play. Some people might be perfectly fine with 2 roles, user and admin, and that's good enough. Other people need fine-grained permissions, like, am I allowed to contact this user between the hours of 8 a.m. and 5 p.m.? There are a lot of different security scenarios that can be represented via scopes. It's entirely up to you. Traditionally, the scope property in a token is a space-delimited list of permissions or roles or whatever you want it to be. The good thing about scope is that the client can inspect these claims. They can look inside the token if they understand the JWT format, base64 URL, decode the text value, and they can look at the scope. And that's nice because let's say the scope says admin. Well, the client can look at that and say, oh, this person's an admin. I'm going to show them an admin button where they can click it and jump into the admin screen. So the client can actually customize itself based on what's in the token. Now, of course, it's really important that just because the client shows an admin screen, it doesn't necessarily mean that users see admin data, right? That screen should be rendered by talking to the server to get that data, and the server, of course, has to do the enforcement on, say, the admin route or URI. The server should always assert permissions on a request. So you can't just assume that because there's a token, they can visit a particular URL. The server always needs to assert that the scopes in the token are allowed to be used for that particular URL or URI. And you can use that via any assertion framework that might be available to you in your language of choice. If a request, an authorization request fails, 403 is the correct status code. And 403 forbidden means I may or may not know who you are, but I'm sorry, you're not allowed to access this particular endpoint with that particular method. Forbidden means even if you're authenticated, you're still not allowed to do that particular operation. So 401 again is around authentication, proving identity. 403 should be used for access control denied statuses. So that's it. We covered a whole lot of information. I'm sure there's going to be plenty of questions. If you're curious about Stormpath, try it out. Give us a shot. You'll see a lot of the things that we're talking about today in practice. One of the things I want to represent for Stormpath actually is we have already built the OAuth servers and token management systems for you. You can do token creation, token revocation per application level. We are an API key server. You can do API key creation, management, rotation. All of that stuff can be done within Stormpath. You don't have to build any of that stuff. So all the things that we've been talking about today, you get out of the box with Stormpath, and you can just drop them into your applications. So hopefully that was beneficial. You could kind of see the implementation paths of what we talked about today. But I'm happy to open the floor up to discussions. Rami?
All right. Thank you so much, Les, for taking us through that in-depth talk. Thank you also to everyone who's already sent in questions. We have some good ones to start with here. So heading back to access tokens and token auth. So if the header is not recognized, can the dev pass the token as a parameter?
So the question is, if the token's not recognized, can they, maybe as a header, can they pass it as a parameter?
Yeah.
The answer is it depends. The authorization header should always be accepted in every web server, or at least every web server I've ever seen. The authorization header is viable because that's spec compliant. So I would be surprised to hear that there's a server that does not accept the authorization header. And so for the most part, you should always be using that. If you do use the token as a request parameter, that's very risky because a lot of services log these things, and so or log request parameters for statistics, for HTTP access logs, and so if that token is logged to a log file, and somebody was able to get access to that log file, they can then use that token and impersonate users, because typically bearer tokens give you full access as that user for however long the token is alive for. You know, that goes back to the whole 5-minute versus half a year conversation. You know, however long the token is alive for, people can use it. So if you do it as a request parameter, we actually kind of advise against that because of the logging issue and the ability to expose it to third parties. What OAuth does is they'll actually use, in their implicit flow, you can actually get access to the token in a URL fragment. Basically, if you look at a full URL and you'll see a hashtag in there, aka octothorpe or #, anything after that is accessible only to a JavaScript client, for example, and not visible in the page and not actually sent to the server. So that data won't be sent to the server, and so OAuth 2's implicit grants will, when redirected back to the user, can have that information in a HTML fragment after the hashtag, and that won't be sent to the server and it won't be logged. So if you have to do it as a request parameter, we recommend that you only do it as a fragment, basically after the hashtag in the URL. Other than that, and actually in most cases, definitely stick to the header if you can. It's spec compliant, it's standard. web servers and HTTP caching and proxy servers all expect that to go through. And most web servers these days will not log the authorization header because they know it could contain sensitive information. So you get all those benefits if you can stick to the header. Remy?
Alrighty. And then will some other type of auth method supplant OAuth 2 in the near future?
The question is, will another scheme supplant OAuth 2? Is that the question?
Mm-hmm.
It's always possible, right? New authentication methods can come out every couple of years. There was OAuth 1.0a, and that was fine for a few years, and then OAuth 2 came out, and there's no. And actually, as part of OAuth 2, there is a new MAC RFC to create digest-based OAuth 2. It's still in its infancy. It's still in draft spec status. It hasn't been approved by the IETF yet. But yeah, I mean, you can have any number of schemes over a period of years come and go. So, but that's possible, but there isn't anything that I've seen to date where that is the case. So the newest, most, I guess, common thing around authentication schemes is really OpenID Connect, and that doesn't change anything. It's really just an extra set of functionality on top of existing OAuth behavior in the OAuth 2, or rather OAuth 2 behavior, OAuth 2 protocol. So HTTP authentication schemes can come and go over time, but I haven't seen anything new that leads me to believe that we'll see anything in the next couple years beyond OpenID Connect that seems to be handling most people's concerns after OAuth 2.
All right. Moving on to digest schemes, we have a question from Niels. For digest auth, is it necessary to store the unencrypted password on the server? And does that imply a security risk?
Yeah, both the client and the server need they need to reference the same key. However, you can use RSA digital signatures, for example, to create, or RSA keys to create digital signatures. So the server could represent or create a digest with a private key, send it out to the client, and the client can verify it with a public key, but the client, because it doesn't have access to the private key, cannot create their own digest and send it into the server. So there are ways around that of maybe negotiating and dynamically generating symmetric keys at the time that the handshake occurs. But what a lot of people do is they'll typically create a shared key, some long random string, and then they'll use encryption in the server to fully encrypt the value using a derived key, and then storing that encrypted value, not the raw value, in their database. And every time that they reference it in their app, they decrypt it before referencing or trying to compute the digest. So yeah, digest algorithms do require the raw value to be accessible to both the client and the server, but there are ways of simplifying that with encryption and also encryption at rest. So yeah, that's a good point. That should probably be as one of the concerns in the pro cons of digest-based schemes. That said, it is typically easier to keep those values secure than it is sending open passwords and such over raw network stacks and through maybe public infrastructure. That typically tends to be a little bit more controlled and will have a little bit more curation around storing encrypted values than public transit or network transport.
Okay. And then also with the digest approach, when passing digest over the wire, what's to stop someone from, hijacking like a man in the middle over HTTP, the digest value and just using that for future requests to the server?
Well, that's the great thing about the digest approach, is that the digest value isn't used for anything other than to verify the digital signature. So the server will get that digest value, and let's say a man-in-the-middle attacker looked at the digest and it I don't know, replaced one character, or maybe made the digest shorter than it actually was. A man-in-the-middle attacker can do that, and then when the server receives the request and the server computes this, goes through the same algorithm to compute the digest, it'll take a look at the digest that's in the request, and in this case, presumably an altered one by an attacker, and it compares it with the digest value it calculated, and it will see the attacker's value is not the same as what the server calculated, and so the server will immediately reject the request. It says, oh, the digest I calculated is different than what's represented in the request. I am not going to trust the request at all. And so the beauty of digest schemes is that no raw password is sent over the wire, and any man-in-the-middle attacker that tries to manipulate any part of the request that has been signed, the server will reject it. And actually, there's a funny story about that in our history. Some of our customers are on Google App Engine. And Google App Engine, and we didn't know this at the time that the customer started using us, Google App Engine, unfortunately, manipulates the request headers. And we had no idea that they did this or even why they did it. It just felt incredibly stupid. We were very frustrated with Google. But when Google App Engine app would make us call out to Stormpath using one of our SDKs, the Google App Engine request executor would manipulate the headers, or I think removed one or added one. So by the time the Stormpath API received the request from our customer, we noticed that these headers were missing, and the request was manipulated in transit, and we rejected every request. The customer could not talk to us because Google effectively was being a man-in-the-middle attacker. They were manipulating the request without the customer or Stormpath knowing, and so our algorithm caught exactly the thing it was designed to do. Nobody's allowed to manipulate the request other than the client and the server. And so digest schemes solve that problem in a very clean and easy way. If the server can't compute the same value that's in the request, then the request is rejected. And it works very well. Again, if you can undertake the complexity of digest schemes.
Okay, and then what about man in the middle simply stealing the digest without modifying the request?
Yeah, there's no problem with that whatsoever. So a digest, kind of like a password hash, is a one-way transformation. You can't look at the digest and reverse engineer it to figure out what the original shared secret was. So that's the reason why digest schemes don't need HTTPS, is the digest value can be seen in the public. It's kind of like an RSA digital signature in that anyone in the world can see it, but only the person who has the private key is the one who can create the signatures. So it's not considered sensitive or secure information at all. Anyone in the world can see a digest because presumably with number theory it'd be sufficiently improbable that anyone could brute force reverse engineer that value back to the original shared secret. So maybe there's a little fuzziness around that with quantum cryptography, but that is so new and cutting edge, and 99.9% of the world don't have access to something like that. So it's effectively out of scope for this discussion, but for everyone else, other than maybe the NSA and a nation state, digests can be seen in the public and not have any security implications at all.
All right. Back onto token auth. Do we need to manage multiple tokens to allow a variety of requests against the same host? And how do we do that?
You can do that, actually, if you want. So you can have different tokens represent different permissions, and you can use one token against certain URIs and another token against other URIs. And that is entirely based on how you represent the authentication request. So maybe you post to that token endpoint and you specify these are the scopes that I want to be enabled for this token, and the server can say, okay, well, I'm going to give you all these scopes, and then you can do another post to get another token with different scopes, and the server can return with a different token. Stormpath, if you use Stormpath for token management, you have the ability to create as many tokens as you want for that particular customer. You can revoke individual tokens as well as refresh tokens. So you have that capability in your app to define which permissions are associated with which tokens, if that's something that's beneficial to you. If you don't use something like Stormpath, you have to figure out how to associate or how to create the tokens and how to associate them with user accounts specifically for the different permissions that are of interest to you. And that's purely going to be part of your token endpoint implementation to figure out which permissions to associate with which tokens based on who the user is and what they're trying to do.
Okay. And then onto authorization. So using a fine granular authorization scheme, will it blow up the scope field, and will JWT still be usable with that?
It's a good question. It depends on how many permissions or scopes that you assign to a user. Like I said, there's a whole lot of apps that do just fine with two scopes, either admin or user, and that's good enough for many people. If you have hundreds of thousands of permissions, then yes, that's going to blow up your scope significantly and make your bearer token huge. Most web servers these days don't want the entire request headers to be more than 8K, maybe 16K in some web servers. So you have to keep that into account, and also they have often limits on any one header value of not being, say, greater than 4K or 8K in and of itself. So you really want to try to keep your tokens as small as possible, just to keep things smooth from a data transmission perspective. If you have more than, I don't know, it depends on how many scopes that you have, but if it starts to blow your token up to greater than 1K or more in size, maybe 2K, then you might want to consider about using a local security framework that uses local caching that says, based on this user, I can just look up a cached representation of all their permissions when I need to do that. Security frameworks in different programming languages support this, or at least give you a framework to help you build it yourself. Apache Shiro is a Java security framework, for example, that uses permissions very well and will do that stuff and calculate that inside your app at runtime. I'm sure there's security frameworks. Maybe Devise and Ruby does something like this. I'm not sure, but it's gonna, at that point, if you have that many scopes, you're really gonna be at the mercy of whatever your local security framework supports.
Okay.
So try to keep it small.
Yeah. And then just to be clear on that, JWT scope is an auth placeholder, not an auth implementation, right?
Right. It's just a list of the permissions that your app makes sense of. So, in my app, I could have, create user, I don't know, buy a TV. Your apps can be anything. Or sorry, the permissions can be anything that's meaningful to your application. The scope field, as defined, or at least that people use in JWTs, is traditionally just a space-delimited list of strings, and those strings can be whatever you want that's meaningful for your application.
All right. So let's see. So if I want to limit authentication to just the API key, so no username or password for an API, what's the best approach using Stormpath?
Stormpath actually has API key authenticators built into its various SDKs. And so if all you have to do is just call the API key authenticator object in the SDKs, or you specifically check the API key against Stormpath, and that's it. In other words, you wouldn't have to use any of Stormpath's username password-based mechanisms. You get to pick and choose depending on what parts of our API or what part of our SDKs that you want to invoke. And if you don't want to support username and password authentication, you just don't call the username password authenticator. It's that simple.
Okay, awesome. Let's see. So does Stormpath support random state strings and scope parameters?
So state, most definitely. So state, especially like a single sign-on flows where you want Stormpath to automate single sign-on between Ping Identity or Okta or any of those guys, or the OAuth 2 stuff. State is always supported in all of those flows, and so there's no issues there. If you want to specify custom scope for your JWT, you can easily repackage the JWT that comes back from Stormpath and just add scope to it before you send it out to your clients. So your JavaScript mobile apps or what have you. And then you can check that on every call into your local application. So Stormpath supports both validation against the Stormpath API as well as what we call local validation that happens inside your application. And you can choose either of those approaches depending on what works best for you. But the scopes can be customized as you see fit inside of your app code base. And we actually have frameworks and hooks into our libraries that allow you to do that pretty easily.
All right. So when you're securing a REST API with untrusted clients where the end user is anonymous, what do you recommend? How do you recommend securing the REST API?
Well, in that case, the best thing to do is to code your REST API and to allow certain anonymous access based on your security rules. So, like, clearly, if like registration, for example, like if I post a /register, I have to be able to do that if I'm anonymous because the system doesn't know who I am yet. So clearly, anonymous users need to be able to register for their website or for their web application. So, in that way, your server-side code that you have should allow anonymous calls into that one endpoint, but probably not any of the other endpoints. So maybe login has to be anonymous, right? Because you're not logged in yet, so you're technically anonymous. Login and register and forgot password. But anything else other than those things that should be enabled to anonymous users, your security layer in your application, whether it's a Java servlet filter or a security framework or Node.js middleware or any of these things exist across programming languages, that security framework should be asserting on every request if you're allowed to make a call to that particular endpoint or not. And the anonymous routes in your app should be left anonymous so that people can do things anonymously, like login and registration are perfect examples. So it's really up to your security framework to enforce that based on if they have a token or not. So if they don't have a token, they're anonymous. If they have a token, then you can enforce certain security rules based on who they are and what scopes they have.
Okay, and then a question from Akshit. How can a single access token generated once by the user be used to authenticate the user for several microservices without requiring generation of tokens again for communication between the microservices?
So that's an interesting question. So it's my belief, and I think a lot of other people's belief in the security world, that a token that's associated with a user, coming from the user, maybe a mobile device or what have you, when it goes into your initial web infrastructure, that token is supposed to represent that particular user, and it's digitally signed in a way that makes sense for that first receiving server. If that server is going to take that token and then send it to various microservices, that's a different interaction. So from end user to your REST API, and then from your REST API to different microservices behind your REST API, those are different audiences. They're different people. It's a different use case. So in that scenario, we actually strongly believe that there should be different tokens for those scenarios. In other words, maybe the user invokes your REST API with one token, and based on that, you can generate a new token that can then be used to communicate with the other microservices behind your REST API. And the reason why that's important is that a machine-to-machine communication path is different than end user to your REST API. Maybe there's shared secrets between those machines. Maybe each one of your microservices has an RSA signing key, and they can use the RSA digital signatures for the JWTs between machines. There are security reasons for keeping that independent of the user key. A big reason is that maybe your microservices don't have the shared, and this is probably the biggest reason, your microservices often do not have the same shared key or user password that was used to create the token that's shared between your client tier and your REST API. Right? You don't want your microservices to have access to those secrets, ideally, because it's an orthogonal concern. It's not related to getting the microservices to function correctly. So we strongly believe in actually using different tokens for different security workflows. You shouldn't be using the same token across all of your infrastructure, because that requires your entire infrastructure set to have access to the same security keys to validate the digital signatures on the token. And you should never, ever, ever accept tokens that you can't verify. So we've seen many problems when people, like we host and run a JWT library called JJWT for the JVM. And we've seen people trying to use the same tokens that come in on the user tier and send them all back to their microservices. Well, the microservices cannot verify the digital signatures because they don't have access to those user keys, and they shouldn't. Right? It's a security issue to expose that user key to every piece of your infrastructure. That's a bad idea. You're cross-pollinating or polluting concerns across your entire infrastructure set. That is not a good practice. And so we try to really discourage people from using the same keys everywhere. Yes, it's super convenient if you think about it, because you can just forward it with every request to every microservice, but you're really opening yourself up to a lot of security implications if you do that. So it is extremely trivial to take in a JWT that comes in to your REST here and just create a brand new JWT based on that to send to your microservices. Like, JWTs are lightweight, they're easy to calculate, they're not, you might add like a millisecond, not even that, maybe a few nanoseconds to create the second JWT, but that's going to be a more secure approach to talking to microservices. So hopefully that answers the question. Granted, this is an opinion of ours, but JWTs were meant to identify users in particular scenarios, and the scenario of a REST API to a microservice is different than end user authentication, most definitely.
Okay. So can you compare and contrast public and private certificates using use with single-use signed and encrypted SAML assertions? PII data is contained in the SAML, and the SAML can be sent in the header of the body of a post over HTTPS.
Yeah, SAML data is usually, especially in the redirect bindings, always sent over posts to get data into a server. Stormpath automates all the SAML and OAuth exchange between third parties, and so I'm trying to see where this question is coming from. As a customer of Stormpath, you never have to see SAML, you never have to see the body. Anytime a SAML assertion comes into our infrastructure, we convert it into a JWT or account representation that then gets relayed into your application. And the PII or data that comes in from the SAML assertion, you can map into a Stormpath account record, and then you can choose which account fields to represent in your application or not. So you have full control over what fields are exposed, what you consider PII or whatever, because you don't actually get the SAML assertion into your app. You get a reduced or simplified JWT, and then you can use that to pull the information you need based on who that user is. And so that's the Stormpath scenario, because we automate that for our customers. If you're trying to do this yourself, yeah, you have to be aware of what is PII, what is not PII, what you want to copy into a JWT, what's considered secure or insecure information. But all of our JWTs at Stormpath avoid that problem entirely, because we represent the subject as Stormpath's unique identifier, which is just an ID. It's public information. Anyone can see it. It doesn't matter, because you have to have security rights to even be able to resolve that ID into actual information. And that's fully controllable by our customers. So if you don't use Stormpath, you have to do that yourself. You have to figure out a way to expose certain properties or not. And do you expose all of them? Which things are PII or not? That's going to be a coding exercise for you to determine, based on policies, what data can be exposed or not. And JWTs ideally should not represent PII or security information safe that could be seen by third parties. Ideally, it's just a small number of attributes, maybe like an identifier, a first name, maybe something else that's not considered PII that makes it easy to render user interfaces, and then everything else can be resolved if you have the appropriate permissions.
Okay, awesome. And then Dan had a question. Have you identified any good patterns for stepping up authentication? So for example, when accessing an API, If the user is logged in and the client has a token, but for a specific API, the authentication is not good enough, and you want the user to be able to provide another password or PIN before proceeding.
Sure. I mean, this is something we're actually working on now, trying to simplify this and turn it into a framework for developers in their own apps. But this basically amounts to checking permissions and or rather, let's say that a user authenticates with a REST API. The way that they authenticated, like the means by which they authenticated, was it username and password, was it API key ID and secret, what IP address did it come from? All that information is relevant to how they authenticated, and that information can be stored in a JWT. And if a particular endpoint requires more assurance than what's currently represented in a JWT, then then they can hold on a second. They can represent that information by, or rather, acquire that information by redirecting the end user to a login page or a new page that requires that additional level of assurance, whether it's multi-factor or some kind of phone verification or what have you. That can be done by redirect workflows to a user interface, and then once they get that information, a new JWT that represents that new state can be used for subsequent requests to the REST API that represents, the means by which they authenticated. It's even stronger than their original way. So that was kind of a roundabout way of saying that you can use redirect workflows to request that information from users when you need it, and if they can't give it to you, then you can just reject the requests.
Okay, thanks, Les. So we have a question from Benjamin. So his company passes user credentials like user token and other details in the request headers, and they use HMAC SHA1. Are they up to date with industry standard?
I'm sorry, my network cut out on that last question. Can you just repeat the question real quick?
Yeah, no worries. So if we're using if we pass user credentials like user token and other details in the request headers, and we use HMAC, SHA1, are we up to date with industry standard?
So if I understand correctly, you're sending personal, I guess, identifying information in the request headers. HMAC SHA algorithms basically just verify the authenticity of the data, that it hasn't been tampered with, that whoever created that data, that it actually came from that person or that entity. So it doesn't keep any of that information secure. So as far as industry standards go, there's a few of them, right? There's SAML, there's OpenID Connect. There's various different flavors of how to get information into and from a server for tokens, but most people advocate sending that data in the request body, because that typically request bodies are usually not logged by web infrastructure, and so it's typically safer than putting them in headers. All HMAC does is guarantee that the data hasn't been tampered with or changed in transit. So we typically recommend submitting data in posts, because remember, with HTTP spec, posts are idempotent, right? They can't be repeated by caching servers, and so you don't have to worry about caching issues and collisions. So if you can post the data in the body, that's a lot better. And yes, the data in that body should be digitally signed with an HMAC SHA algorithm, preferably SHA 256, if not greater. Hopefully that answers the question.
So I think just to clarify a little bit, that actually, no, that does answer the question. Benjamin, just let us know. Okay, awesome. Thank you. So that's all the time that we have questions, all the time that we have for questions today, everyone. Thank you guys so much for joining us this morning. If we didn't get to your question, please reach out to our support team. They're really good. They have really quick response times. You can just email support@stormpath.com, and they'll get back to you. Just a reminder, we'll be sending out the recording and slides in just a little bit, as well as any other reference material we went through. So keep an eye out for that. And yeah, thank you all for hanging out with us through that awesome presentation and Q&A session. Hope everyone has a great rest of your day.